Hello, thanks for joining. We'll get started in just a moment here. All right. Hello, everyone. Thank you so much for joining us today for this webinar. This is the second webinar in this series with USGS and the National Water Availability Assessment. This webinar is about communicating the science with data science and visualizations. Before I hand things off to our speakers today, I want to give a brief overview of Quasi while folks are getting settled and logging in. My name is Julia Masterman. My pronouns are she, her, and I am the training coordinator for Quasi. Quasi is a consortium of universities for the advancement of hydrologic science incorporated, and we're a nonprofit funded in part by the National Science Foundation. Our mission is to empower the water community and advance science through collaboration, infrastructure, and education. We sustain infrastructure to enable research and collaboration and host data repositories for water science data, specifically HydroShare. By providing this support and infrastructure, Quasi hopes to help researchers formulate and execute their data management plans, be effective data stewards, and meet the requirements of funding agencies. We also provide a suite of educational opportunities and infrastructure for student and early career support. These include workshops, a summer institute for graduate students, webinar series and events like this one, a virtual university, and more. Both our data infrastructure and training opportunities are designed to enable collaboration and interdisciplinary work. A few upcoming deadlines to point you towards. Firstly, the Water Prediction Innovators Summer Institute is a partnership between Quasi and the University of Alabama, and it aims to engage the academic community in research to advance water prediction. And we are currently accepting applications for both the theme lead role and the role of fellows. So theme leads advise student teams on research projects throughout the summer. Fellows are the graduate students who do the work, who are in research teams working on projects relating to the themes dictated by those theme leaders. Applications for both of those roles, as I mentioned, are open now. If you have any questions about either of those, please feel free to reach out to me. There's also more information on the Quasi website. But we're always blown away by the quality of work that comes out of 7 short weeks over the summer in Tuscaloosa, and also the impact that this program has had on the careers of its participants. You'll also find Quasi at AGU this year. It's coming up quick. So Quasi and the AGU Hydrology Section Student Subcommittee will be at booth 836 in the exhibit hall. We'll also have a reception, community gathering, one of the nights of AGU. So if you find yourself there, please come find us at the booth and RSVP for that evening gathering. More information is on the Quasi website, and I'll share a link in the chat in just a moment. We invite you to connect with us, join our mailing list, or connect with us on various social media platforms. A link to that QR will be in the chat in just a moment as well. And now for a big announcement. So as you all, as registrants of this webinar series know, the second, what was originally to be the second webinar in this series was postponed and has now been rescheduled. So if you rejoin on December 10th, that is when we will be hearing more about leveraging the science with the data companion. So that webinar has been rescheduled. You'll receive the connection links the same way you have for all other webinars in this series. And you'll also, anyone who's registered for this series will also receive an email from me letting you know about this new webinar date. But we're glad that we're going to be able to hear all 3 webinars in this series and that we were able to be flexible in the scheduling there. All right. So today's webinar is on communicating the science with data science and visualizations, and a huge thank you to our speakers today. A few logistics as we get started here. This webinar is being recorded and will be posted on the Quasi YouTube channel. Secondly, we ask that you use the Q&A functionality to submit questions to our speakers. Please feel free to add questions at any time and upvote any that are especially of interest. We'll do our best to get to as many as possible at the end. Finally, we expect that all involved with quasi-cyber seminars uphold the quasi code of conduct and promote and maintain a professional, considerate, and collaborative virtual environment. So thank you for being a part of that. And with that, I'll stop sharing my screen and pass the mic on to our speakers to introduce themselves and get us started. Thank you so much again.
Thanks, Julia. Let me share my screen here. Does that look right on your end?
Yep.
Okay, great. Thanks. Okay, so thanks, Julia. My screen's here. All right, so thank you for joining us today to learn a little bit about the behind the scenes work that Anthony, my co-presenter, and I did to help communicate the science of the National Water Availability Assessment with both data science and data visualizations. I also want to take a moment to thank the other co-presenters in this cyber seminar series, Shirley, C, Jennifer, Meg, and Ted, and we are all part of the Water Resources Mission Area at the USGS. In addition, I want to thank all of the other USGS co-authors of the assessment as a whole for working with both Anthony and I through this process. As a quick introduction to myself, my name is Althea Archer. I'm currently a science communicator in the Water Resources Mission Area at the USGS. My background is in forest ecophysiology, environmental consulting, and academia. My role at the USGS is mainly to help translate USGS water science into visuals, blogs, social media, presentations that engage and educate the American public. And I'm joined today by Anthony Martinez. Anthony is a data scientist in the Water Mission Area. His background is in forestry and fire ecology with prior work at the U.S. Forest Service. His role at the USGS is to help disseminate water science by helping teams build robust data pipelines and training other data scientists to further our mission to create transparent and trustworthy data. I'm going to start by very briefly talking about the National Water Availability Assessments and then kind of expound on what my role is and what Anthony's role is in this wider assessment project. So in January of this year, USGS scientists published a multidisciplinary National Water Availability Assessment report, data companion, and an interactive VizLab website. So today we're focusing on the behind the scenes effort to write the report specifically, which includes chapters such as water quality, water supply, water use, integrated water availability, and so forth. I won't go into any more detail on the findings of the report itself. So if you are interested, but you missed the prior cyber seminar on the report findings in September, that video is available on Quasi's Cyber Seminar Archives page at that link here. And you can also go to this QR code that will bring you to the USGS landing page, which allows you to kind of connect to the report, the data companion, or the VizLab website. So today, instead of talking about the findings, let's think more deeply about what it means to write a comprehensive report about water supply, water quality, use, availability for the entire lower 48 United States. So I'm going to start with a little thought exercise. We're going to imagine a lone researcher, which, as probably most of us would say, is actually pretty rare these days, but stick with me anyway. The researcher collects data, does some exploratory data analysis, creates some exploratory visuals to understand those results, runs statistics and models, writes up a report or manuscript, chooses a few key figures from those early figures, and then polishes all that up and has some final report, final manuscript, maybe a thesis, and so forth. Let's make things a little bit more complicated and more like real life. We're going to add in the collaborators, some collaborators in another data set. Now the number of exploratory figures increases. More people are involved in the writing of the final report. In the end, agreements are made and a finalized report is created, again, with those polished visuals. To complicate things a little bit more, let's talk about the figures that are created and the analysis that gets conducted. Let's say a couple collaborators work in R, a couple work in Python, maybe a few are more comfortable in Excel. This is still not too big a deal. Probably you would tackle this type of project with some dividing and conquering. We have some revisions at the end, get things to look and read harmoniously, and then all's well with that final report. But what happens when you have this many contributors, including 24 separate authors, all contributing to a report that has 7 chapters with over 100 figures and is over 450 pages long? If we put ourselves in the shoes of one of the lead scientists of this National Water Availability Assessment report, we can imagine that they would want to follow much of those same steps as some of those earlier slides. They want to work on the science in their field. They want to do their exploratory data visualizations, run their models, and then focus on their conclusions, interpreting their results, and doing the writing for their section or their chapters. Of course, then get feedback, revise, polish, and then eventually publish. So the problem is, a few things can make this task more challenging when you're working on such a large-scale interdisciplinary project. For one, each team approaches analysis and modeling with their own preferences. Maybe it's how they approach using p-values or the programming language of their choice. Maybe it's the colors they use to represent data on their plots, or maybe it's the time scales or the spatial scales at which they're working. Another similar obstacle is how to handle interoperability within and amongst research teams. Everyone approaches writing and analysis and design differently. Each person brings their own set of soft skills. So this diversity in approaches enriches a report and science in general, but can make it difficult to bring everything together into one cohesive report. This can be as simple as code sharing between two folks when one uses base R and the other uses tidyverse programming, or it can be more specific, such as varying versions of packages or operating systems. And then there's always the obstacle of how many different revisions and reviews go into this type of large-scale project before publication. When it comes to the revisions with so many different contributors, this can get very tedious with all those manual tweaks to individual charts or models or text. So ultimately what this means, instead of just focusing on the technical side of their task, such as the writing and the interpretation, scientists are caught up in seemingly endless revisions and manual tweaks to bring everything together. And this is where Anthony and I come in. So you can think of Anthony as the data analysis wrangler. The scientists do a lot of their preliminary analysis and models, but work closely with Anthony to incorporate the data analysis, modeling, and statistics into a reproducible data pipeline. That's what he'll be talking about today. And then you can think of me as the data visualization wrangler. I work with the scientists and with Anthony to guide the data visualization design and think about the whole report cohesively. And that's what I'll be talking about today. So together, our goal is to allow the scientists to focus on the more technical writing and interpretation tasks rather than the coding and designing logistics. The end result is a much smoother process for all of us, easing the way for the report to go from draft through all those reviews and to publication and ultimately into your hands. So I'm going to pass it over to Anthony now to talk about charting smoother data streams with reproducible data science.
Cool. Let's see. Thanks, Althea. All right, so before we continue, I want to talk about what reproducibility is and why it's important. Reproducibility can mean a lot of different things, but here I'm going to use it in kind of just a general sense to basically mean that given a set of inputs, we can recreate the same outputs, whether that's numbers or figures. And we do this primarily by preserving the steps in our workflow in code, and we're assuming that code runs without issues. So this builds confidence in the results of our analysis and trust in our science, which is hugely important to us. Our code will produce the same results when it's run across our sessions, on different machines, by different users, and across time. This adds rigor and transparency to our results. Others can run the code and our workflows for related tasks, others can run the code themselves and get the same results. It also improves the usability of our analysis. We can use pieces of our code and our workflows for related tasks, cutting costs because code takes a lot longer to write than it does to run. We can use code in one project as a pilot for a workflow and then adapt it and reuse it for other projects too. Next slide. There are a few things we can do to improve the reproducibility of our projects. I like to think of reproducibility as having a lot to do with isolating different aspects of the analysis from external threats. So, so what I'll be talking about are isolating your workflow, and I'll address this by organizing files, isolating your computations by writing functions, isolating your environment by using pipelines, and reproducing your environment by managing the packages and package versions. So let's dig into each one a little bit. So I think the biggest bang for our buck is in isolating our workflow. We want to ensure that the work we're doing for a project is not unexpectedly influenced by other projects or our work on other projects. This is primarily addressed in your file system and by the way you organize your files. Files shouldn't cross project boundaries. This minimizes disruptions to your projects by ensuring that analysis from one project doesn't interact with analysis from another project by adding, deleting, or modifying files that are common to both sets of analysis. So to do this, each project has its own directory. I think this is probably the most important part. In this example, water supply has its own directory, and water use has a different directory or folder, and the files or code in each of these don't reach into each other's folder. Within a project folder, you can organize files in any way that makes them most useful for you or your particular project. I think a good generic approach is to have subfolders for your inputs, where you would include things like your raw data files, which should be read in, but those raw data shouldn't be modified. Your outputs, and these are the things produced by your analysis to be used elsewhere, like reports or presentations or things. And then your source code, which contains any of the programming code that you've written that's used to produce the results. Projects only access files from within the project directory they are in, or from external sources like websites or databases. But most importantly, they don't touch files from other projects' directories. So here, water supply is not grabbing any data from water use. If you need, some sort of common file, make sure to duplicate it. So there's a copy in each of your project directories. A good way to help make sure that you're not touching files that you're not supposed to in R is using R Studio projects. These help ensure that all the file paths are relative to the project directory so that it's difficult to reach outside of your project directory and mess with files from outside of the scope of the project you're working on. Once our files and workflows are insulated from one another, then we can start to think about isolating our computations. When writing code, one of the most basic ways of doing this is by encapsulating our discrete analysis steps into self-contained functions. So just writing your own functions. This can help break down complicated ideas into manageable pieces, and it helps us conceptualize our workflow into discrete steps. It keeps your global environment clean by reducing the clutter of many intermediate variables and can allow for easier debugging. Maybe some of those terms don't make that much sense, and that's okay. Just know that it can help keep your programming a little bit cleaner. In some cases, a lot cleaner. Functions facilitate code reuse, which reduces duplicated code. Writing code in this way can help organize and tidy up our code, and it provides good opportunities for documenting code and testing assumptions that we're making along the way as we write code. All right, so here's what this can look like using R code. In this example, on the left pane is kind of the before, and in this case, we may want some summary statistics for nitrate concentrations and water supply data. We start kind of that first line by creating some dummy data, which is just nitrate concentrations for water samples. We then are calculating the mean, standard deviation, and if it exceeds some water quality threshold. We then assign the value of each of these to a variable. On the right side is what I'm proposing you use. So we start by creating a function, and in this case, it's called nitrate summary. And it takes nitrate data and whatever your exceedance threshold is as an argument or as arguments. Then it computes the same summary statistics in the body of the function. And then the function outputs a named list of values with the mean, the standard deviation, and whether it exceeds the given threshold. So all the calculations are all the same. At the bottom of the right pane, the function is run and the list of value is saved as a single variable. So this is what it looks like. It's a little bit of a simple example to illustrate what it could look like, but oftentimes custom functions would contain a lot more code that do a little bit more complex tasks, although not always. And while this is more lines of code, we've decluttered our global environment, so we're not producing all these extraneous variables. And we've produced a reusable function that will aid the reproducibility of our work throughout our analysis. Next. So I may not have sold very well how good of an idea writing functions is, mostly because that's not like fully within the scope of this talk. But take a look at these blog posts I've written. And they're all about how to write functions in R. In them, I do a little bit better of a job expressing the importance of writing functions, and I give instructions and tips on how to write effective functions in R. All right, so now that we've isolated our workflow and our computations, we want to isolate our runtime environment. So what this means is that you want to run your code in a fresh session of R or Python. A common anti-pattern in data analysis, so something that we often do, even though it's not a great idea, is that we save the state of our sessions. So we're keeping previously computed variables. So we created a data frame, or we have the mean of some values saved. And then we close out of R or Python, and then we open it back up, and all those things are still preserved in our environment. Well, this may seem like it might save a little bit of headache of rerunning code. This can have a substantial negative impact on the analysis because it relies on arbitrary or ephemeral results from previous computations that are not tracked by a linear workflow. So it could be impossible to reproduce these because it relies on steps that are not written down in durable code. We solve this by running code in a new session. So every time we want to run our code, we solve this by running code in a new session every time that we want to run our code. This forces us to write down all of the parts of our workflow in code, which can be rerun. By rerunning everything from the beginning, we ensure that we are capturing all of our analysis steps in code, but this could be potentially time consuming and inefficient to continue like rerunning everything from the start. So this is where the next part of my proposal comes in, which is using a pipeline tool, also generically called a workflow management software. These are things like the targets package in R or the snakemake library in Python. These run code in a new environment so that your code is unaffected by the state of your global environment. Again, if this doesn't if that all sounds like word salad, that's okay. Fully understanding that at this point is not that important. So anything you want to keep saved is written down in code that produces it. I think that's the important part. So targets works by tracking your code and the outputs from your code and only running the pieces of your code that are out of date or incomplete. This means that you can rerun an entire workflow or an entire pipeline, and it only runs the part of your code that needs to be run. Right, next. So running your code in a fresh session is a super important part of reproducibility. And again, I probably haven't fully convinced you of that here. But there's a prominent figure in the R community named Jenny Bryan, and she's spoken a lot about this topic over the years in some pretty like inflammatory posts on Twitter and things like that. But she goes into this and a lot of other great topics at length in an ebook that she wrote called What They Forgot to Teach You About R, which is available at that website, rstats.wtf. All right, next slide. Yeah. All right, so the targets package in R works by building by building a dependency network, which is a type of network graph. This represents the output of every step in your workflow as a discrete object called a target. You run a single command in R and it builds the entire workflow. If you make a change to an input file or the code, Targets detects those changes and reruns only the affected pieces of your workflow that have become out of date. SnakeMake in Python work, you interact with it a little bit differently, but both are derived from the same earlier like software ancestor called new make. So fundamentally and conceptually, they're very similar. Okay, so here's an example of a dependency graph for a workflow, and this is produced by Targets. The end result of this workflow is an interactive HTML map and a static map image. And each one of these circles represents an intermediate step of a workflow to produce those maps. Let's say I make a change where the arrow is pointing, and, oh wait, go back one. Okay, let's say I make a change to a part of the workflow, and that part of the workflow filters out streams that are to be mapped in the final output. Okay, now click. So what used to be green circles representing up-to-date targets now become blue for the targets that we changed, and then all the steps downstream of it, because those are all affected by an upstream change. This is letting us know which of these are out of date and need to be recomputed. So when we run the pipeline, which we do with a single command, only the pieces that need to be rebuilt will be rebuilt, and all those unaffected parts of the pipeline will be skipped. All right, so the final step is to reproduce your environment. What I mean by environment in this case is the software that's running your code. This includes which software packages or libraries that you're using, and also the package versions. If software or software versions change between iterations of running your code, you could get different results. If the way we address this is to use code to define our environments. In R, typically you'd use a package called renv, and in Python you'd use something like Pixie. renv documents your packages and package versions that you're using within a project into a file that's similar to an environment.yaml or a requirements.txt file if you're using conda or pip in Python. You can share these with collaborators or your future self, and this file will, with the help of renv, reproduce pretty closely the environment that it was created in. One bummer is that it can't support software that isn't in our package. So if you're using some external piece of software, like a command line utility or something, renv can't track that. But renv does work mostly in the background and can be initialized and used with just a couple of lines of code. So you can, it's really powerful and can do a lot of things, and it's not a ton of work to implement. All right, so it's important that you think through the benefits and the risks of using each of these techniques and how they relate to the needs of your project. Each of these techniques requires some different expertise to use, so the balance between reproducibility and the technical expertise of those performing the analysis must also be considered. There's always a limit on resources, whether that's time, money, the availability of technology, and the skills and experience of the team. So these must be considered also when evaluating which techniques are used. Each project and the team and each team is going to have different needs. So your approach must be tailored to your situation. All right. All right, Althea. So why don't you let's talk about data visualization.
Okay, thanks, Anthony. I'm going to talk about communicating clear and cohesive messages with data visualization in a little bit more detail. So, as a little bit of background, this project, the National Water Availability Assessment Report, had been ongoing for probably over a year by the time I kind of came onto the project. And that meant that a lot of the science had already been done, and a lot of work had been done to produce models and analysis and data sets, and a lot of even reproducible pipelines were already in place. And that also meant that there were a lot of intermediate figures that had been produced. So basically, each chapter and then maybe each sub team within a chapter had their own figures already. And I was coming in to provide this idea of cohesive design across all of these chapters and all of these figures. And so one of the things I noticed right away was that a report like this really needs to have a place names map. The goal with this map is to orient readers to the hydrologic regions. So when you're reading and you read something like Midwest hydrologic region or Columbia Snake hydrologic region, you really need to know where that is, especially in relation to you. And so there were several of these maps that were created by each sub team when I started. And this is one that's kind of more like cartographic, really pretty. Also contains some called out aquifers as well as these regions. Here's a really simplified one that's actually pretty easy to read if you look at it like in full resolution, but it doesn't have the states on it. Here are two that had this color encoded approach so that there was a legend where you could go from the visual to the legend to figure out what the name of the hydrologic region is. One of these has states on it, one doesn't. And then the color schemes are different between the two. And also, these color schemes actually are pretty commonly used for either a wet, dry, or a hot to cold temperature gradient. And so it's a little bit confusing to use those for places that don't have that particular type of gradient other than east to west here. And then here's another one. This one is also pretty kind of classical cartography, and it has some of those underlying regions that aren't actually the hydrologic regions that we were using. So it has that kind of spurious information that's detracting from the takeaway. So the solution for this one, and this is a good time to plug Anthony and his cartography skills. He actually ended up making this map in the end. And also iterate that I did not produce all these maps. I'm not the one doing the work to make all these viz. My role is really to wrangle and help bring together the cohesive approach to design. So I did make some data visualizations, but in a lot of cases, I just helped guide the researchers to make the visualizations more cohesive. So in this case, the solution was to create one visualization that would work across all the chapters with no spurious information. And particularly what's cool about this is that it does use color to encode these regions, but then these colors are actually providing naming and color cohesion for corresponding visuals. So now in subsequent visuals, if we have something where we want to show data by region, we can actually use these same colors. This map is clean and legible. The hydrologic regions are directly labeled. It includes states outside of CONUS, which is important for some of our visuals. And the states are represented here, but as secondary information, there's no spurious information here to take away from that main communication goal. So now let's look at another example. Visualizing water use. In this case, we have three categories. We have irrigation, public supply, and thermoelectric water use, and then two sources of that water, either groundwater or surface water. So when we are talking about data visualizations across a big project like this, of course, we need to have cohesion and kind of a shared approach. And when I started, again, so much of the science has been done already. There were a lot of versions of plots, like showing water use by region or water use by year. Here's one of these examples. This is fairly small. I know it doesn't matter that you can really read it. I'm just going to point out some features about this one in particular. Because I'll show you then what the final graph looks like. So here we've got 6 different colors. Those are encoding those 3 supplies and then the 2 sources of each supply, so public supply, irrigation, or thermoelectric. And then the takeaway here is really comparing water use across regions. And that's what's on the x-axis. These are grouped bar charts by region. And one of the takeaways for this section, for example, irrigation groundwater is that green color, the kind of neon green, and then irrigation surface water is that yellow. One of the takeaways is that irrigation, groundwater sourced irrigation, is one of the largest water use categories for the Western United States. But you'll notice that in this graph, the regions are actually alphabetically located. So it goes high plains, northeast through Midwest, southeast, and then western. And when we look at charts and regions, we actually expect western regions to be on the left, working our way from west to east. And so it's actually really hard to pull that finding out of this particular viz. I'm going to pause on that now and just show you some other water use viz that have been created. In this case, it's more by year and a different color scheme, and even a different color scheme between these two visuals. So for instance, irrigation is brown on one of them and then blue on the other one. So we just obviously need some cohesion across these. So one solution that I came up with right away was to start creating what I call a style guide. So here we want to have cohesive colors that we can use across all the chapters and all these data visualizations, but we also want them to match thematically. So an example here is the brown and the goldenrod colors used for irrigation water use. I chose those colors because they're reminiscent of the idea of like a wheat field. And so they kind of build this connotation in somebody's head about irrigation, crop irrigation. Public supply, I chose reds because in the National Land Cover data set, urban land is often represented with red. So we have this kind of idea that urban and public supply might go together. And then we can use these colors across chapters. And then also this helps you make sure that you're not double encoding a color. So we're not going to use the same blue that we're using for thermoelectric saline water use that we're using for precipitation, for example, in a different chapter, a different visual. And then this helps make everything look more cohesive, but it also makes things accessible because we can choose colors that have a high enough contrast ratio to help work for people with low vision. So here's one example outcome of this type of cohesive data viz. This is a map for public water supply because it's red. You could get that at a glance. And the way that the values here are encoded is using shade. This is really nice and makes sense for accessibility because you can actually print this in black and white and you can still read it, or you can look at this if you have no color vision whatsoever and actually still read it, which is really nice. Okay, so now I'm going to go back to that viz that I showed you earlier and show you how rearranging data, it actually makes a really big impact. Here we are looking at the 3 different water use categories separately, and then we're looking at the lighter color is always surface water and the darker color is always groundwater. And now our regions are also placed geographically, so they go from the west to the east as you read from left to right. You can actually see now the dark brown columns there show that geographical distribution of groundwater sourced crop irrigation, which is one of the main points of this visual in the report. So this helps make the relevant comparisons easier to read at a glance, and also, again, uses that cohesive color scheme. The other thing that's really cool about this is directly labeling these bars makes it so that this is an accessible plot, whether or not people are able to differentiate these colors. So I'm going to go through some tips for success really quickly. I already mentioned this. Having a style guide is really important. It's really great to have a cohesive style guide that informs colors, styles, standards, anything that's related to the design. This style guide should be considered a living document. So when you say we had thermoelectric water use as a blue, but then we realized we really need to differentiate saline thermoelectric water use versus freshwater thermoelectric water use, we might need to add a whole nother blue. So you want to keep these style guides as a living document as you go along. And then it's also important to follow contrast and color best practices, again, using those thematic colors that we already can read. Using red for hot or urban land is one example of that. Another tip for success is thinking about layout across all these data visualizations. So setting standards for aspects such as legend format and location. Where is the legend going to go and how is it going to look? Where are you going to put what we call OCONUS? So those are Alaska, Hawaii, Puerto Rico, et cetera, on maps, if you're going to include them at all, if they don't have data. What projections are you going to use? And then we used in this report this type of grid or facet arrangement fairly often to make sure that all these small little mini charts had a geographical layout. And so setting that up early on and then using that consistently across visuals makes it a lot easier for the readers. You can also, if you're using something like R, it's pretty easy in ggplot to share thematic elements with custom templates across projects and share with somebody like Anthony who's working with the data analysis as a whole. And then workflow. Anthony already said this. I will reiterate. Reproducible code-based programs make data visualization process, the whole process from analysis to visualization a lot easier and a lot better. It allows for better sharing, a lot more efficiency in coding practices, and much easier iteration and transparency. And then, of course, that means fewer headaches down the road. This is, I will say, I will reiterate even more that this iteration process is so much easier. I already mentioned that there's so many revisions and reviews and revisions. And one thing that happens really well when you have a reproducible code-based program, a workflow, is that if we decide in the end or a reviewer says you cannot use that blue for whatever category, you need to use a purple. And that doesn't really happen. But if you want to change a color, for example, because I'm talking a lot about colors, you can just change where that's defined in this pipeline. And as Anthony showed, only, let's say we're changing public supply water use color, we change it upstream, and only those figures that have used that variable in the data will change. You don't need to rerun every single visualization. This also means that you're not going to miss any visualizations and accidentally send something out to publication that has the wrong color. And I also really think that it's important to peer review code and design along the way. And I'm just going to reiterate how important it is to build in time to iterate. It is really important to make sure that you have time towards the end to fine-tune visuals across a project like this. Having a lot of critique sessions is really nice, and evaluating the body as a whole is really valuable. So this is one final example of an actual visual from the report. This is one that that existed when I started, and it's a very polished visualization. It is showing the water quality impairment status of principal aquifers across the United States with those little pie charts. And the main takeaway is that there's a regional difference in the high concentration categories. The high concentration categories here is the yellow. When I saw this, I think it's beautiful. But my thought was, okay, if we want to use a cohesive design approach, let's use the pink, this kind of pinkish purple, a very unnatural color. This is the color that we chose to show impaired waters when we're talking about water quality. Let's use a dark value of that for the high category and a medium value of that for the medium category, and then kind of a neutral color for water that's not as impaired. And then my feedback was, can the aquifers in the be in grayscale to make the pie charts pop better? Since the colors for the aquifers aren't defined anyway, outlines or grayscale would be okay since they're directly labeled. That was my feedback on the actual chart itself. And here's the final visual. And I think this is really a good example of how just a small amount of iteration can really make a big impact. When you look at this, it's a lot easier to see where those punchy dark purples and light purples are, what areas of the US have higher rates of impaired waters. And the aquifers are there, you can still see them, but they take a step back visually from the data itself, the important data, which are those pie charts. So this brings us back to where we started this presentation, with some obstacles that stand in the way of letting scientists in a project like this do what they're good at, the science, the writing, and the interpretation. And we've shown you a few ways that you can improve your approach by making more consistent approaches to analysis and visualization across research teams, by improving your coding practices to ensure interoperability, and then definitely ease the revisions, reviews, and more revisions process and make it work a lot smoother and with fewer headaches. So with that, I think Anthony and I are ready to take some questions. Again, I will plug if you're interested in learning more about how you can access the data that goes into the National Water Availability Assessments, that webinar on December 10th, we'll be talking a lot about the Data Companion, which is an online data portal so that you can access and use those data in your research and your own data visualizations. And please follow us on social media.
Thank you so much. We're waiting for questions to roll in from the audience, but in the meantime, we had a few questions that were already answered, and maybe we can speak more to it for the sake of the recording and the audience who may have missed it. So just to reiterate, how to optimize, the first question we have is how to optimize your workflows using AI tools. What do you recommend and what might be some concerns?
Oh yeah. Yeah, so I wrote a long thing, but to say it verbally, we are like kind of constrained in which AI tools we're allowed to use at USGS just because of the nature of working for the federal government. But that said, I don't know, I have some like kind of general off the cuff thoughts, even though you could write a lot of papers and a lot of papers have already been written about this sort of thing. So um, I think we could use just kind of general AI coding assistance to help us speed up the code development process, writing code faster, writing code better. A lot of those like are not super well developed all the time yet. Like a lot of the code that is produced by those is pretty verbose and I don't know, sometimes a little bit overly complicated, but they're always getting better. So that's just kind of like a general thing we could do. We could also build tools. I hesitate to use the word vibe coding because that's probably not a good idea, but use AI to help us build tools like R packages or Python libraries or things like that to ingest and summarize new data and come up with with quick insights. We can also feed data directly to some of these AI models and have it summarize things for us. I think those could maybe be helpful for just getting kind of like the broad strokes of what is in the data. AI tools, one thing that they are really good at is seeing patterns that people don't see very well, and so that sort of capability could be leveraged with kind of clever prompting with a data set, probably not too big of a data set. But doing that can be really expensive to buy all the tokens required to do some of these AI like computations, I guess you'd call them. But those could be potentially offset by if that's saving you a bunch of development time that you're not spending banging your head against the keyboard. There are also considerations about security, like the security of your data. All this stuff generally, unless you have like firewalled plans with different AI providers or you're using locally hosted AIs, those go to the company to be used to train their models and things like that. So there's that aspect of it. And then finally, you don't want to do any of these things without independently verifying that what the AI is doing is right, whether that's, results. That one's super dangerous to rely on AI to come up with, but also, building tools. There may be bugs hidden in the tools you're building or the packages you're building that are making assumptions that are not reasonable or that are not testing things the way you think they are. So you have to be really careful with all of these things. But I mean,
Yeah,
there's tons of cool opportunities.
yeah, thanks so much. I also want to point the audience to a lot of the great links that were shared throughout the course of the presentation have been shared both in the chat, and then also if you click to the answered tab in the Q&A, you can access those links there as well. Althea, there are quite a few questions coming in for you, specifically about how you receive feedback on your visuals and getting review um, from folks and input. So do in your tips to success, iterate. You mentioned the importance of building in those moments for review from the beginning. Um, and then there's quite a few great questions. Who do you invite to participate in those reviews? How far ahead of time do you schedule them? And how do you change, or how do you handle changes in availability? Do you tend to set up synchronous or asynchronous reviews? And how do you help folks and yourself avoid feeling like you're missing things because you've looked at the document so many times?
There's a lot there. I this all started with, again, a lot of the science had been done. And the first thing I did when I was about to this actually happened with Anthony and his predecessor like invited me to one of these meetings. And um, I I kind of had to sell how important cohesive data visualization is to this research group because they were worried about the science. They weren't worried about the data visualizations. That's my job, right? So um, I came to this presentation. One of the first things I did was I actually just opened a PowerPoint and I took from every draft, I took a copy of the visuals and I made one visual on each slide that just went through. It was like, here's chapter one, here's chapter two, here's chapter three, and here are all of those all of those um, versions of every graph that exists right now in the draft in one place. And that was when I found it was really easy to see, for example, okay, every chapter has their own place names map. And there's a ton of different approaches. And so it was a lot easier for me then when I came back to the research team and said, hey, we have all these different versions. Did you even know? And in case, maybe the water use team didn't know that also the water supply team had also made a place names map. And it was like, oh, well, duh. Okay. So my role was really to take that step back and like look at everything as a whole. And that made my job in kind of um, justifying cohesive design a lot easier. When somebody just sees five different versions of a map, you can kind of point out the best features from each one, and then somebody like Anthony can come in and create a really good, nice, harmonious version that has all the pieces that you want. Um, and then the other thing I actually did kind of early on, this was the manager's um, Ted Stutz. He actually invited me to kind of come to each team individually as more of a consultant role. And so for that, again had all these PowerPoint slides for each section, and I said, let's look across these. This is what I'm seeing. Um, it is hard with critique that you don't want to make things personal. One thing I always say is make it solution focused, rather than, than chewing up what's wrong with something. Talk about how something could be improved, and just making it, spinning your feedback in that way can make it a lot easier to swallow. Um, and then in some cases, it can be difficult. There can be um, a lot of back and forth because there may be things I'm not a subject matter expert in something like precipitation maps. And in some cases, there may be, let's say we're talking about drought, and I'm like, oh, use these colors for drought. The author might say, well, we actually want to use these colors because this is what the national drought maps use, and that's what people are used to. And then I go, oh yeah, I didn't think of that. Okay, let's adapt the color scheme. And so it's just important for both the critiquer and the critiquee to be open-minded, I guess. As far as like logistics of this, um, there is a lot of room for both synchronous and asynchronous feedback. In a lot of cases, I use synchronous feedback times to kind of show and walk through visuals like that PowerPoint and say, okay, here's what I'm seeing, here's some issues. But then asynchronous feedback where I'm just like putting those notes on the slide and saying, can we use these colors? Let's rearrange these regions geographically instead of alphabetically. And then that, that's just a source for when the data scientist or the researcher is actually making the visual, they can see that written down and just kind of do the work then. So I think there's room for both asynchronous and synchronous. I think I got most all of those little pieces of questions in there.
Yeah, no, that's great. You mentioned kind of answers that also speak to a few other questions we have. So, um, how do you logistically navigate the coordinator's suggestions for standardization and an individual contributor's opinions? I understand that can be tricky. So yeah, keeping it solution focused. It's a great advice.
Yeah. And sometimes I have to say, sometimes showing is better than telling. And so in some cases, I actually would just get the data. If it's something like the geographical, um, the west to east aspect ratio, like putting the regions alphabetically versus geographically, it might not seem like that makes a difference, but once you see it, it really is like, oh, well, you're right. That does actually make a big difference. And so doing that through like having examples to show is sometimes a lot more powerful than just me telling somebody that has been working at, in the field for 20 more years than me what to do. So that can be a delicate um, conversation. I just also have to keep an open mind and be willing to be flexible as well.
Yeah, thanks.
Mhm.
Okay, one more. There may not be a good answer for this one, but do you have resources or recommendations on how the audience can get feedback on their visuals or data visuals similar to the critique that you provide for the National Water Availability Assessment? Um,
That is a really good question. Honestly, depending on the sensitivity of something, I think social media is a really good place for that. Um, because you will get feedback. It may not necessarily be considerate feedback, but you will probably get some good feedback. I think, when I was a grad student, uh we kind of created, not within my lab, but all the grad students in the department would kind of come together for these little pseudo fake presentation times, and that's a really good time for feedback, where you can say, okay, I'm going to give you just like the 3-minute thesis version of some of my plots and get feedback that way. Um, Peer-to-peer review is always kind of the best way to go because you see things in other people's graphs that you don't always see in your own. Another thing that really helps is printing out your own plots and looking at it on paper. Sometimes that just makes you realize what's standing out and what's not, more than when you see it all day long, every day, pasted into a Word document or something like that. So those are some ideas I can come up with off the top of my head.
yeah, no, that's great. Um, all right, Anthony, thank you so much for answering some of the questions that are coming in by typing in answers. A number of great resources have been shared. Um, Tools to ensure contrast between colors and accessibility in visuals, some favorite tools, program softwares to use to enhance visuals and graphs and maps. So thank you for sharing those.
And I'll put one more plug in for our blog. It's waterdata.usgs.gov/blog. We have a lot of data science blogs on there, really nice ones that Anthony already talked about and has written. And then we also have a lot of blogs on there about data visualization approaches, including reproducible examples that you can follow along with. So it's a good place for both data science and data visualization, especially related to water data.
Great. Thanks so much. All right, we are at the top of the hour. Um, Thank you for your time, Althea and Anthony, and for taking the time to present today. I really appreciate it. And a reminder, join us on December 10th for the last webinar in this series. Thanks so much, everyone. Have a good rest of your day.